When a bright red fishing lure hits the water, our human eyes see a vibrant flash of color that shatters the surface. We treat color as a permanent property of an object, but this perception stops at the waterline. Once submerged, a lure is subject to the unforgiving physics of the water column. Waiting below is a highly evolved teleost predator, the largemouth bass. Its visual system is a biological computer, extracting information from this low chromaticity medium. Anglers spend hours agonizing over specific paint colors to trigger a strike. However, the fish is reacting to an entirely different set of environmental data. To understand the hunt, we must look past human eyes. In the deep, survival is dictated purely by the mechanics of attenuation and contrast. As the red lure descends past the 20-foot mark, its color is physically stripped away. The vibrant red vanishes, leaving a dark gray mass. This process is governed by the Beer-Lambert law. Water molecules and suspended particulates absorb low-energy, long-wavelength red light within the first few feet, while higher-energy blue light penetrates much deeper. This chart displays the illuminant spectrum in clear water at depth. The black line represents available light, which drops to 0 in the red spectrum, above 600 nanometers, while peaking sharply in the blue range at 450. Because the environment lacks red photons to reflect off the lure's surface, it effectively loses color. It becomes a stark black silhouette against the surrounding water. This microscopic section of the black bass retina shows the architecture of a duplex visual system. It contains both cone cells for high-resolution daytime vision and rod cells for extreme light sensitivity. In darkening water, the eye undergoes retinomotor movements. Daylight-sensing cones contract out of the light path, while sensitive rods elongate forward to capture every available photon. This physiological handoff from color sensing to the rod-mediated system is known as the Purkinje shift. At this stage, the predator is functionally colorblind. It can no longer perceive hue, only varying levels of brightness, making contrast the primary trigger for a strike. Predators hunt from below, looking upward. From this angle, an object is reduced to a black shape against the bright background of Snell's window. Species like the walleye use an additional biological advantage to hunt in these depths, a reflective layer behind the retina called the tapetum lucidum. This structure acts as a biological mirror. Light that passes through the retina without triggering a receptor is reflected back for a second pass, effectively doubling the eye's sensitivity to light. By combining internal light amplification with the silhouette effect, these predators turn near total darkness into a high-visibility hunting ground. Fluorescence is the only optical mechanism that allows color to exist in deep water, where it should be physically impossible. It relies on the Stokes shift, a quantum process where a material absorbs a high-energy, short-wavelength photon, like the blue light penetrating deep into the water. The material instantly re-emits that energy as a longer wavelength photon. To the fish, the lure glows with internal light. Because fluorescence generates its own photons rather than reflecting them, it allows a lure to maintain a chromatic signal after standard pigments turn black. At its final depth, the lure is a dark silhouette vibrating against a murky background. This shape and movement is what finally triggers the strike. The success of this hunt had nothing to do with the specific paint color on the lure's surface. It was a reaction to pure contrast and water displacement. In the shifting landscape of the underwater visual field, color is a luxury of the shallows. Contrast is the ultimate ruler of the depth.